Just to reiterate something I mentioned in the lab session this afternoon, for those of you who thought you were going to be in the afternoon lab and recitation section and you're actually in the evening, and for those of you who are in the afternoon and wanted to be in the evening, yeah, just send an email to myself and Dr. Gagreb, and what we'll do is you'll need to drop the class, which sounds a little scary, but we'll immediately give you an add code to add to the correct section. So tell us whether you want to be, whether you want to switch afternoon for evenings or the other way around. And we have some add codes for you to be able to switch them over. Okay. So it shouldn't be that, hopefully shouldn't be that difficult. We still have some people on the wait list, but if you're already registered, it shouldn't be a problem just to switch one section to the other. Okay, so hopefully don't worry too much about that. All right. Can hear you eating dinner. Man, I'm hungry already. Okay. So to just pick up where we left off yesterday, a lot of, if you're following along with the slides that I've posted already, I'm probably going to go through the rest of chapter 1 fairly quickly because it's stuff we've addressed either in recitation or in lab, stuff about significant figures and things like that. And we're going to get, hopefully we'll get started on chapter 2 today and actually start talking about chemistry rather than, you know, boring old math and stuff like that. Okay. So just finishing out the rest of the units that I'm going to be dealing with. The standard unit for mass in the metric system is the kilogram, which sounds weird. I mean, it should be the gram, right? Because it doesn't have a prefix in front of it, but it's actually the kilogram. And as we mentioned in lab this afternoon, it was originally the kilogram was originally defined as the mass of a liter of water. Pure water has 1 liter of it has the mass of exactly 1 kilogram, which is why the density of water is precisely 1 gram per mil, or 1 kilogram per liter. After that, it was then defined by this piece of metal, which is bizarre. But really for like 200 years, it was defined by the mass of this certain piece of metal. It was platinum iridium, and it was kept in France under 3 different holders. And then 2 years ago, it was redefined in terms of Planck's constant. We'll talk about Planck's constant when we get to talking about light and quantum mechanics and that sort of thing. But I just wanted to mention that it's only been 2 years since we've had an actual definition of the kilogram that can be used to measure anywhere on the planet. As you can imagine, before, if you wanted to standardize the measure of a kilogram all the way around the world, you had to make a standard, you had to ship it to France, and then it had to be compared to the mass of the kilogram there, and it was ridiculous. So now we have a system where we could standardize the measurement of a kilogram no matter where you are, anywhere on Earth. This is what it looked like. This one is a replica in Maryland, the National Institute of Standards and Technology, or NIST. And you can imagine the problem of having a standard like this. I mean, because it's sort of kept away, and it changes slightly based on, you know, whether or not it's undergoing some sort of chemical reaction. That's why it's under so many glass holders on top of it with all the air pumped out. Because if you could imagine, if it oxidized, then it would gain the mass of oxygen, and then it would no longer be a kilogram. So we kind of got rid of that ridiculous system a couple of years ago. As far as temperature goes, we mentioned this yesterday, but the official unit is Kelvin. You don't really use it anywhere else outside of science. You're not going to be listening to the weather forecast, and they're going to have a Kelvin mentioned as the temperature. But the reason why the standard unit is Kelvin, because there's no negative temperature. It starts with 0. It just goes up. And when we're dealing with energy, all energy basically stops at 0. All kinetic energy stops at 0 Kelvin. And so it's the base temperature for dealing with any sort of chemical calculations. Celsius was used, it still is obviously, used for metric for, I like to call them civilians. But scientists use Kelvin because anytime we're measuring a change in energy, generally we're talking about changes in Kelvin. So like I mentioned, Celsius degrees are the same magnitude as Kelvin. So if I said, what's the difference in Kelvin between 23 and 25 degrees Celsius? The answer is 2, because the units are exactly the same. It's just where they begin. So water freezes at 273 Kelvin and it boils at 373 Kelvin. So there's exactly the same number of degrees in between. So if you want to convert the units, fairly straightforward between Celsius and Kelvin. Just add 273 to your Celsius and you're good to go. In Fahrenheit, we're not really, the only time we talk about Fahrenheit is in the actual temperature outside in the United States and a couple of other countries, but we don't mention Fahrenheit in chemistry because nobody measures temperature in Fahrenheit. If we were in the lab and measuring temperature, we would have a thermometer that registered it in Celsius, and then we just convert it to Kelvin. But Fahrenheit, I remember in Canada when we would change to the metric system in the late 70s, it freaked everybody out because it was like a warm summer day. It was like 80 degrees, and now it's only 26, and it took some people a while to get used to it. But now everybody's completely used to it. And here's just quickly how to do it. If you have Fahrenheit, you just multiply it by 9/5 at 32. That gets you to Celsius. And if you want to go from Celsius back to Kelvin, you just add the temperature of Kelvin at 0, which is 273.15 Kelvin. So again, you won't have to memorize this. If you take you can look it up if you're doing a test, or I'll also post pages where I usually would keep all of these relationships, so you wouldn't have to memorize them. In fact, I'll do that this weekend. I'll post that all on Canvas. It'll just be like a handy place that has all the information you'll need for doing tests and things like that.
I have a question. On the test, are we allowed to have those formulas with us or no?
Of course. Yeah, I'm all about not memorizing things. That's why, like I said, I would if you were taking a test in class, I'd give you I think it's like a 5 or 6 sheet guide of all of the conversions. So you don't have to memorize any of that stuff. I just want you to be able to do it. So know how to use those conversions rather than memorizing, oh my God, 273.15. I mean, who's going to, I can remember that. Only because I've been doing it for 30 years. But yeah, you don't need to memorize any of this stuff. Just acknowledge and see what the relationships are. So this shows you all the differences in Fahrenheit, Celsius, and Kelvin. So you can see that at -40, which it gets to places like Minnesota and Buffalo and certain parts of northern Canada, -40 Fahrenheit, -40 Celsius are both really damn cold, and they're the same temperature. But once it starts to rise, you can see that the Fahrenheit, there's a lot more degrees. There's a lot more degrees in between. And so between 32 and 212, where water boils and water freezes, there's 180 degrees Fahrenheit, but there's only 100 degrees Celsius. And with Kelvin, same thing. Remember, that's the most important thing to take away from all of this, is that 1 degree Celsius, 1 difference degree Celsius is exactly the same as 1 Kelvin. And so if you're given a problem with, water cooling from 100 degrees C to 40 degrees C, and you're calculating how much heat is involved, you can use a difference of 60 and not have to worry about remembering exactly what the amounts are in Kelvin. Just know that the difference in Celsius, the difference in Kelvin are exactly the same. So you don't even have to worry about that 273.15 thing. So these are how we derive some of these units. And this is important because it's good to know when you're calculating volume, where those numbers come from. And because one thing that's constantly coming up is, what is a liter? How do you measure a liter? One would think that since the standard unit here for the standard unit for volume is the cubic meter, not the liter, which is strange. I mean, because liters is really what we measure everything in, the volume of everything in the metric system. So you would think, okay, well, a cubic meter must be a liter, and it isn't. 1 cubic decimeter is a liter. And so that's actually 10 centimeters cubed. So 10 times 10 times 10 is 1,000. So 1,000 cubic centimeters is a liter. Hopefully that'll stick a little bit, because you remember everything in the metric system is in tens, 100, 1,000, million. So a cubic centimeter, and you can even sort of imagine what a cubic centimeter is like. A centimeter is about that big. So you imagine a cube, if there's 1,000 of them, that's a liter. So 1 cubic centimeter is the same as 1 ml or 1 mil. So a lot of times density will be given in terms of grams per cubic centimeter. And you look at that and say, what the hell is that? I don't know what that means. Well, because we've been in your lab today, you will be calculating, or have already calculated, or will in the future, whatever. You'll be calculating the density in grams per mil, or grams per milliliter. Just remember that a cubic centimeter is exactly the same as a milliliter. So if you're given, a lot of physicists and engineers talk about grams per cubic centimeter, but it's the same thing. So a cubic centimeter and a milliliter is identical. So don't worry about that. So again, here's just to give you an idea of what the volumes are like. So you can see that a cubic meter would be huge. That would be a really, really large volume. It'd be like 1,000 liters. And so 1,000 liters of water would be extreme. That would be 1,000 kilograms. That's like a ton. So a cubic meter of water would weigh a ton. So it's really, really big. So a liter is basically, if we divide this into tens, which is what they've done here. If we divide this into tens and just took, divide this into 10 centimeter units, then, and that's 1 liter. So you can see that it's really, really big, 1,000 liters. So 1 cubic centimeter is a mil, and it's a little smaller than a dime. So that's the sort of sizes we're talking about, okay? So density, we've been blathering about density a lot. Just mass over volume. It just tells us how much stuff there is in a certain volume. And the standard unit for this is kilogram per cubic meter, but really we don't really use that very often. Like I said, what we generally use is gram per mil or grams per cubic centimeter. But you'll notice that you pretty much get the same thing. Since there's 1,000 cubic centimeters, and you multiply this by 1,000, you multiply that by 1,000, you pretty much get the same thing, but we're used to looking at density in here. Like I said, commonly used density units for solids and liquids is this one. For gases, which are really, really not very dense at all because there's so much space in between the molecules, generally we give density in grams per liter. But when you're talking about much more dense things like liquids and gases, it's grams per mil or grams per cubic centimeter. Okay. So I have a piece of ore that contains lead. It has a volume of 4.6 cubic centimeters. Okay. So I've got a lead mine, working in a lead mine, not an easy job. I get this piece of ore. It's 4.6 cubic centimeters. Now, if the density of that is 7.5 grams per cubic centimeters, what's the total mass? So how would we do that question? Fairly straightforward. I stupidly did not bring my calculator with me, so someone's going to have to give an answer for me. How do we go about it?
It's 0.6133.
Okay,
So you plug in the equation, density equals mass over volume. So you plug in the density as 7.5 grams over cubic centimeters.
Mm-hmm. So how many grams is that?
How many grams as in mass?
4.6 times 7.5. How many grams does that give us?
Oh, sorry, 34.5 grams.
0.5 grams. So, but that's not what we're looking for, right? We're looking for kilograms. So how do we, what's this mass in kilograms?
You multiply it by 1,000.
I don't multiply it by 1,000.
Divide it by 1,000.
Yeah, so again, you would go, I want 1 kilogram over 1,000 grams. Yeah, and yeah, you wind up dividing. So it would be 0.0345 kilograms. Is that right? 1, 2, 3. Yes. So 0.0345 kilograms of lead ore. Okay. So like I said, I'm going to sort of go through this fairly quickly because we talked about it a lot in lab. So there's a big difference between counting and measuring. If you get a dozen eggs, there's no uncertainty about that. You have exactly 12, unless you go to a bakery and maybe 13. But if you're buying a dozen eggs, it's 12, exactly 12. So you would write down, if you wanted to know how many significant digits there were in a dozen. So 1 dozen would equal 12.00, and I could just keep going forever because it is exactly 12. It's not, an estimate of 12 or it's fairly close to 12. It's exactly 12. So anytime you have something that's exact, it basically has an infinite number of significant digits. So like a foot is exactly 12 inches. It's not 11.9-ish or 12.1-ish. It's exactly 12. And so that is it's an exact number. Strangely enough, like I mentioned yesterday, 1 inch is exactly 2.54 centimeters. This is weird how that worked out, but it's exactly that. And a gram is exactly 0.001 kilograms. So if I have, if I've measured a gram to 5 significant digits, I've also measured my kilograms to 5 significant digits. I don't have to worry about changing my number of significant figures when I have an exact relationship between units. So foot, inch, gram, those things are precise. They're exact. I don't have to worry about changing them. When I'm measuring, however, that's different. Any other quantity other than counting are going to be uncertain. They're going to be estimates, right? Because whenever we measure something, that last digit is an estimate. Even if we have 15 significant digits, that 16th one is still an estimate. And so those numbers are not exact. They can be precise, but they're not exact. There's always practical limitations. So anytime you measure anything, you have to report it in some way that indicates how precise you were, how uncertain you are about that number. When you're counting, you're not. Like I mentioned, if you have a dozen eggs, everyone understands exactly how many that is. But because you're not measuring it, you're counting. Or a gross of something, or a ream of paper. It's exactly 500 sheets. It's not 499. It's not 501. You're not measuring. But if you're measuring, you have to give some indication of how certain you are about that number. And like I mentioned, that last measurement has to have one estimate. That last digit is always an estimate. And so we have to say, when we're giving that number, when we're writing it out in an experiment or in a test or writing a scientific paper or whatever it is, you have to give some sort of indication how precise that number is. You just can't write the number 3 and expect everyone knows exactly what you mean by that. If you measured it to 3.00005, well, brag a little bit. I was able to measure it that accurately. Don't just write down 3. And we did this sort of exercise this afternoon in lab. When we're measuring the volume of something, we usually measure the volume. If we're measuring the volume of a larger volume, we'll use this graduated cylinder. And you can see this graduated cylinder only has marks for every milliliter, and that's it. It stops. And so what would people, I'll just give you a couple, what would people say that this volume is? If you had to, because remember, you're going to know it's not 20, it's not 21, and it's not 22. So you've got at least 2 significant digits there, but you need to estimate the third. So what would you estimate that volume?
20.5.
Mm-hmm. Okay.
21.7.
Okay. Anybody else? Those both sound pretty good.
The
Yeah.
same as 21.5.
Okay. What I mentioned to the class this afternoon is that generally when you're doing this sort of measurement in a lab, usually you work in pairs. And so what I would do is when you measure something like that, you've got to get down, your eyes should be directly at the same level as the meniscus there. Just get right down on it. And so there's no, you're not looking at it from above, you're not looking at it from below. You can see exactly where the meniscus is. And then you would read it, and then your lab partner would read it, and then you would pretty much average it. And this is perfect because I would estimate that at 21.6, which is right in between the 2 estimates I got. And so it's pretty close. And so that's why this number is uncertain. It's an estimate, but it's significant because we know it's not 21.0 and it's not 22. So we can see that. And so we know any scientist looks at a number like that and they know that it's going to be 21.5, give or take a little bit. It's not going to be exactly that. It's not going to be 0.5, it's not going to be 0.7, it's not going to be 0.6. We don't know exactly what it is, but it's going to be around there. And so that just that number indicates that that last number is uncertain, but it's significant because we know that it's somewhere in the area of that number. And so that's what we're going to go forward with. Just saying that it's 22 without any other number is not a good way of putting it, because we know it's not 22. It isn't that. It's less than that. And so we should, by saying it's 21.5 or 6 or 7, we're saying that it's less than 22, but it's more than halfway. It's like about halfway or so, maybe a little bit more. And that's exactly what we're saying by using the significant digits. So, like I said, if someone said the volume was 21.6, ooh, man, that was good, 21.6. 2 and 1 are both certain, 6 is an estimate, but they're all significant, okay? So I would say there's three significant digits there. And so you need to know the number of significant digits in a measurement that someone else gives you. If someone else measures something, and they, for that particular example, if they gave you a measurement of 22, you would be assuming that that volume would be closer to 22 than it actually is. Generally, if someone gives you, see if I drop something. Oh, here we go. Generally, if somebody gives you a volume, let's say of 22 mils, you would assume that that would be plus or minus 1 mil. So it could be anything between 21 and 23. But that actually, we measured it more precisely than that. And so that's why we say 21.6, 21.5, or 21.7, because we have more precision than this. And so if we have that precision, we should use it, because we'll get more accurate answers when we do our calculations. So just to finish this off, zeros. Sometimes it's weird thinking about when's, or confusing when zeros are significant and when zeros aren't. So any zeros to the left of non-zero numbers are not significant. So these numbers, that one, and that one, are not significant, because basically all they're telling us is how big or small the number is. And think of it this way: if you were to write that number in scientific notation, would you use those zeros? The answer is no, you wouldn't. And if you don't use them in scientific notation, then they're not significant. So if you were to write this number in scientific notation, you'd start at that 4, okay? So the first zeros on the left, not significant. Just placeholders to tell you how big or small the number is. Any non-zero number is significant, obviously, because, I mean, it's there for a reason. It's because somebody used it to measure. Any zeros in between non-zero numbers, like these zeros, are significant because they're between non-zero numbers. So they're there for a reason. Now, where it gets confusing is these trailing zeros. Because trailing zeros are significant only when they're to the right of a decimal place. So why is that? Well, they're there for a purpose. Those zeros were put there because whoever measured this number was able to measure it with those zeros there. Meaning that when they measured it, they measured this value as 0, and they measured this value as 0. That's the only reason they're there. If they weren't measured, they wouldn't be there. So if they're on the right of the decimal place, they're significant. Now, on the other hand, and this is why it's still a little confusing. If you have a number like 104,000, This zero is significant because it's in between two non-zero numbers.
Mhm.
These three are not. And again, just like these zeros over here, the only reason they're there is just to tell us how big or how small the number is. Again, if you would leave those zeros out in scientific notation, they are not significant. And that's all those zeros they are doing, is telling us that it's 104,000. It's not 10,400. It's not 1,040. It's not 104. It just tells us how big that number is. Now, something that you will see that you possibly haven't seen before in other science classes is this number. It won't have a zero, it won't have a like 0.0 at the end, it won't have that, that won't be there. It'll just be like 104,000 decimal place. That has 6 significant figures, because what that means is that these 3 zeros were actually measured. So it's exactly 104,000. It's not 104,001 and it's not 139,999. It's precisely that number. And so we just put a zero, we just put a decimal at the end. And you'll see that on tests and on worksheets a lot of times, where someone will measure 450 decimal liters. That means they measured exactly 450 liters, not 449 and not 451, 450. So there's 3 significant digits in that number. So I hope this makes the point, because I was confused for the longest time about trailing zeros are really confusing.
So, Professor, for this number 104000, if there is no decimal, it should consider as 104?
No, it's still 104,000. It's still 104,000. It just
If
means
there is
that,
no decimal?
yeah, it's the decimal or not, it's still the same number.
Okay.
But if it doesn't have a decimal, what it means is that it's 104,000. It's not 105,000 and it's not 103,000. It's around 104,000. So it's the closest thousand. So it means that something's been measured to the nearest thousand, right? But when I put a decimal at the end, that means it's been measured to the nearest 1. That's the difference. So if it's been measured to the nearest 1, then I need to put a decimal there. And because that will, if, let's say I had 10,000, if I had 104,000 measured to the nearest 10, the way I would do that is I would give 1.0400 times 10 to the 5th. And that would tell me that I was able to measure 104,000 to the nearest 10, okay? Or to the nearest 100. If I left out this zero, it would be to the closest 100. But if it's 104,000 without any decimal places, pretty much all you can say about that number is that it's to the closest 1,000. That's all that means.
Okay.
That's a really good question. Yeah, and it's hard to write down 104,000 to the nearest 10 without using scientific notation. In fact, it's impossible. It's because you can't put a decimal there, because that changes it to a 10,400, right? But yeah, that's a good question. That's why I still find it confusing to this day. All right, so how many significant digits do we have in A?
2.
2.
2,
Excellent. And B, how many significant digits in B?
4.
4,
And you guys are getting this. And in C?
4.
That's right. Excellent. So you see, pay attention to the number of zeros, where they are in relation. And yeah, absolutely right. So we did this during the recitation. I'll just go over this real super quick. For multiplying and dividing, it's different than when you're adding and subtracting. And the reason is, when you're multiplying and dividing, the answer that you get will have the same number of significant digits as whichever number had the fewest significant digits, okay? So we can just do that here. So we have 9.2 times 6.8 times 0.3744. And I put that on my calculator, I get this number. But how should I report that?
23.
23.
Okay.
23.0.
See.
I would just put 23.
23.4.
23. Yeah, because 9.2 and 6.8 only have two significant digits. So basically what that means is that when you're multiplying two things together, you're limited in whatever number has the least amount of precision. Basically, you can't give an answer that has more precision than your least precise number. So whatever your least precise number is, basically it's going to screw up your answer. If I measure something like super, super, super accurate, and then someone says, well, give me about 10 of those, you know, basically say, well, yeah, give me about 10. I've sort of wasted my time basically measuring this super, super accurately because they want around 10 of them. And so there's no point in measuring out 10.00000 times that. I just measure out, you know, a rough estimate. So the same thing is true here. Now it's different when we're adding and subtracting. For adding and subtracting, you're basically looking at the places past the decimal, okay? So if we're adding two volumes, we add them together, and then we look and see which one has the fewest number of spaces past the decimal. So here, we can see that this has 3 significant digits, and this has 4 significant digits. When we add them together, we get a number with 5 significant digits, but really, the final answer should only have 4. And really, all we're looking at is this number. We're just looking at that. So it's one of the few times you can take two numbers with 3 significant digits, add them together, and get 4 significant digits. Because all we're looking at is how many are past the decimal place. And that's where we would do our rounding. So if we added, so if this 23.28 was 23.2896582, and it just kept going and going and going, we ignore all of that because we're limited by that number right there. That 83.5, it's just 0.5, and then it stops. So we don't know what comes after that. It could be a 4, it could be a 3, a 2, or 1, we don't know, or a 0, we don't know. And so we're limited in our precision by that. And so we just do one number past the decimal place. So if you have a complex calculation to do where there's addition and subtraction and multiplication and division, you always do the addition and subtraction first. Then you do your multiplication and division, because this is a little trickier to do because you have to actually physically add them together to see how many significant digits you're going to get. Once you do your divisions and multiplications, it's just a matter of figuring out the total number of significant digits. And I think there's some questions on the recitation worksheet that are involved with that. And when we did them, do the addition or subtraction first, and then do your multiplication and division, okay?
Professor, why
Yeah.
did we only have 4 instead of 3? I still am confused.
Oh, sure. Okay. So when you're adding and subtracting, the only significant digits we're worried about, the only ones we're thinking about, are ones past the decimal place. Okay? So we're just thinking about these numbers here. So when we add those together, we get, so this has 3 significant digits and this has 4. We add them together and we get this number, and that has 5 significant digits. But all we're looking at, we're not interested in this. We're not We're not looking at the numbers to the left of the decimal place. We're just looking at the numbers to the right, because that's where we're limited. We're limited to numbers past the decimal place. And this number only has one digit past the decimal place. So when we get a sum, our sum also has to only have one digit past the decimal place right here. All the numbers to the left are fine because this has numbers to the left, this has numbers to the left. That's whatever. Those are all significant. So anytime you add significant numbers together, you get significant numbers in the sum back. But on the left side, on the right side of the decimal place, our sum can only be as specific or as accurate as the least specific number. And the one with the fewest significant decimal places is 83.5. It only has one, and so we can only use one past the decimal. Okay, does that make more sense?
Yeah, that's better.
Okay. I confuse myself sometimes. Don't feel bad about asking me. So a lot of times I'll be going, wait a minute, that doesn't sound right, and then I'll awaken out of my stupor. And again, this example with subtraction, same sort of thing. First number only has one digit past the decimal place. The other one is 4. Well, I mean, that's great that the other one is so accurate. But if we're subtracting a very accurate number from an inaccurate number, we can't give a very accurate response because we don't know if any of those 3 numbers are right, because we don't know. Remember, this is all blank. We don't know what any of those numbers are, so we can't say there's 0. We don't know. They could be 2s or 3s or 4s or 1s. We don't know what they are, but we know when it was rounded to 0.9. But that's it. We don't know any of that. So all of this stuff has to go because we don't know whether those numbers are accurate or not, and so we just round to one number past the decimal. Okay.
Mhm.
So just rounding, I think you guys pretty much know the rules for rounding. If it's less than 5, if we have to round our last number, the number to the right of it is less than 5. We just leave it. If it's greater than 5, we round up and just increase it by 1. So if we have 996 and we have 0.5, we would round that to 997. If we have 996.4, we would just leave it at 996. Some folks will argue that if you're adding together lots and lots and lots and lots and lots of these numbers together, you would overestimate the sum, which is true, because all we're doing is rounding up, keeping them the same. But we're not going to worry about that too much. That only is a problem when you're adding together, like, hundreds and hundreds and thousands and millions of numbers. That's an issue. So nowadays, we're able to look at, trillions of numbers and do these vast calculations, and it's a problem. And so what people will do is that they will go back and forth between rounding up, rounding down, rounding up, rounding down, rounding up, rounding down, which is important if you're adding together, millions and millions of numbers. But if you're not, if you're just adding together 2 or 3 or 10, use this measure for rounding, the one you've always used. So just some examples. People are pretty much used to doing these. This is just the same thing. The first one, we would round that up to 0.287, because after the 6 is 7. We would round this down. 18.3 because there's a 3 there. We would round this up because there's a 5 there. And we would round that up also because there's a 5 after the 8. Okay, so just use the regular rules of rounding you've been using your whole lives. If some of you go on to computer science, you may learn a different way of doing it. But this is chemistry, not computer science. Okay.
Professor,
Yeah.
I noticed in the book it says that if the number you're rounding is 5, to round it so that it's an even number.
Yeah, that's the method I'm talking about.
Okay.
That's the sort of new method, and we only really use that for summing large numbers, summing large groups of numbers. If you're not summing large groups of numbers, I would not do that. If you want to round like that, that's fine, but it's not required. The only time, like I said, the only time it is required is when you're adding thousands or millions of numbers. You will see that your sum is greater than if you hadn't done that. And so that's the only time it's really an issue. Yeah, I saw that in the textbook too, and I went, who put this in there? That's not what I would have done. But yeah, I'm glad obviously someone's read the textbook. Very impressive. But yeah, you can do that if you want, but I don't do that. I don't know people who do. So that's a new thing. And it's only because we've started this sort of new studies in science. You probably heard omics, right? Has anyone heard this on the end of a word, like genomics and proteomics and all kinds of omics? Have you heard that before? Genomics you must have heard of. No one's heard of that?
Yes, I've heard it.
Yeah, basically, it's because of like new advances in computers and software and hardware. We're able to, instead of looking at the expression of one gene or one protein. I used to work in proteomics, where basically what you want to do is measure the concentration of every single protein in a sample, which 30 years ago would be impossible to do. Hell, 20 years ago or 10 years ago, impossible to do. We can do things like that now. And so you're dealing with these huge numbers. And when you start adding up millions and millions and millions of numbers, this rounding becomes an issue. But when you're not doing that, it isn't. And so when we're simply adding 2 or 3 or 4 or 5 numbers, it's not an issue. But it is now with the advent of omics type technology, where we're trying to measure millions of things simultaneously. But I'm glad you read the textbook. That's a great question. So let's not make it any more complicated than it needs to be. Oh, oops. So just before we finish chapter 1, just wanted to go over this. This is something that a lot of students confuse. I still get confused about it sometimes. There's a big difference between accuracy and precision. People think it's the same thing, and it isn't. So we want to be precise. Any scientist wants to be precise in their measurements. And all that means is that when they repeat them, they get the same answer, or very, very close to the same answer. So if I measured something at 14.7, 14.8, 14.6, 14.5, 14.7, I'd say, oh, that's really precise. I'm getting really close to the same answer every time. So I can take the average of that and be pretty confident that that's what my measurement is. Doesn't mean it's accurate. What's accurate is whether or not it's close to the precise answer, the real answer. So here, basically, we want to shoot at the center of the target. That's really what we're aiming for. We want to be accurate. And we use precision to get there. But you see here, those are accurate. Those 3 shots are very accurate. They're very close to each other. But they're not, I'm sorry, they're very precise, but they're not very accurate. It would be like if a, Olympic shooting champion, archery champion shot 3 arrows into the judge, and all in the same place. That'd be pretty impressive precision, but their accuracy would be really poor. And so you don't want to do that. So you could have a very precise wrong answer. And in fact, if you're going to take analytical chemistry later on, that's something that your professor will nag you about, like mine did. There's a reason why it's called anal chemistry. It's because you have to be very, very precise. When you're doing your experiments, you have to be very, very, very careful. And a lot of times what would happen is that you would get a very reproducible answer that would be completely wrong. And so you'd think you're going to get a really good score on your lab report, and you wouldn't, because you screwed it up. So this is really what you're shooting for. This is sometimes what you get, and this is really bad because you're all over the place. Your numbers are all different, and none of them are right. So what we're shooting, we use instruments that are precise, and when we use them properly, we use them accurately, okay? So you want to get very little difference between each measurement, but you also want accurate number. So here's classic example. You've got a dispenser, probably like in a pharmacy or something, and they're just measuring out cough medicine into bottles, and so they use the automatic dispenser. So the first one gives us these numbers. When they measure the volume that dispenses, you get those. Second one gives you these. Third one gives you these. Which one of those 3, or which of those 3 are precise?
3.
Mhm.
1.
1 and 3.
1.
I'd say 3 is the most precise, right?
Mhm.
Because there's very little difference between them. Very little difference. 1, there's some difference. Actually with 1, most of them are pretty close. These 4 are all really close. This one is off a little bit. So I'd say this, as far as precision goes, this one would be the most precise. That one would be the next most precise. And this one would be the third most precise. But which one's the most accurate?
3.
3.
3. Yeah. Because this one gives you the same answer over and over again, but it's wrong. This one's all over the place. And this one is both precise and accurate. So that is really what you're shooting for. So if I had dispenser number 1, basically all I would probably have to do is just give it a little bit of a tweak. I know it's working properly because it's very, very precise. It's just a little bit off. And so you just give it just a little bit of a, I used to have a really nice robot. And when I have a problem like that, yeah, you just give it a little bit of a tweak, and then it's, so every month or so you would, oh, hello, you still there?
Yes.
My screen just went blank.
Yes.
Where it went. Oh, something's coming back. Oh, there we are. That's odd. Where were we? Oh, here we go. It's weird. Yeah, so Yeah, so your robots are always precise, sometimes not very accurate. So you would do what's, like I said, every month or so, you would test it. Basically, you would measure, you'd tell it to measure exactly 1 mil of water, and then you would basically weigh it and see how close they were. And if it wasn't, you would just give it a little bit of a tweak until it measured out precisely 1.0000 grams. And then you knew it was both precise and accurate. So dispenser 1's precise, not that accurate. Like I said, 2, accurate, more accurate than 1. So it's closer to 296, but it doesn't have that precision. And 3 is exactly what you want, both accurate and precise. I'm pretty much, people know about scientific notation, right? I don't have to go through this. What I was going to do is just sort of go right to, we've got like 20 minutes. I was going to start on chapter 2, if that's okay. And does anyone have any questions about scientific notation? Because basically all we're looking for is scientific notation. You have to have a number between 1 and 10, and with the total number of significant digits we're looking for, and then multiplied by 10 to the power of something. Then yeah, I think pretty much people are familiar with that. So like here, 987,000, only the 9, only the 8, only the 7 are significant, and everything else after it is just basically a placeholder to say how big it is. So we would say 9.87 times 10 to the 5th, because we've moved the decimal place 5 places.
I can say 98.7 multiply 10 over 4.
That's accurate, but it isn't scientific notation. Scientific notation is always a number between 1 and 10. Always. So it always has just, so you have to have a number between 1 and 10. If it's less than 1, then you would just move the decimal over. Do you have something greater than 1? If it's greater than 10, you move the decimal the other place to the left. So you would have a number between 1 and 10. So it's always 1 and 10. That's why. I mean, you would be right. I mean, 98.7 times 10 to the 4 is 987,000. That is correct, but it is in scientific notation. Okay. In fact, there's some questions on the recitation pretty much exactly like that give you numbers that are either less than 1 or bigger than 10 and ask you to fix them. And again, sort of 0.00309, all the zeros until a number shows up are not significant. They're just telling you how big or small the number is. And so the 3 is significant, the 0 is significant because it's in between 2 non-zero numbers, and that last 9. So we just use 3.09. There's some three more examples. All right. So we're going to start chapter 2. Oh boy, it's going to get started and actually talk about chemistry for a change, rather than all this other stuff. So is I guess the subtitles are gone, where people can no longer see the subtitles? Or were you able to see the subtitles before?
Yeah, but now we can't see it. It says
Yeah.
reconnect.
Yeah, I see that too. So yeah, we must have lost a little bandwidth there or something. My son must be like, playing Minecraft or something like that. Anyway, yeah, so we'll start chapter 2 and actually talk about, something important: atoms, molecules, ions, the real stuff. So some definitions. We've sort of been through this a little bit before. Element, just the simplest type of substance with only one type of atom in it. That's it, just one. You can't break it down into anything else. Physically or chemically, you can't break it down. So it's just atoms, okay? single atoms. Sometimes an element can also be a molecule, but if those two atoms are joined together. And that's what you see B is here. That would be something like nitrogen or oxygen or something like that, some gas, hydrogen, where those two atoms are bound together chemically. It's still an element, but it's also a molecule because there are chemical bonds between them. So here, this element doesn't have any chemical bonds between them. So this would be like a noble gas. And over the molecule would be any, what we call a diatomic molecule with the same atom, okay? Now compound, any substance with two or more elements combined together. And they can be the same atom, they can be different ones. So those are molecules of a compound that have two different atoms in them with a ratio of 3 to 1. Mixture can have two or more elements or compounds. We talked about mixtures being either homogeneous or heterogeneous, depending on if you can sample it in different places and get different results from your sample. It depends how well they're mixed up together. So here in B, we've got two elements. Where is my annotations? There we go. So here we've got, yeah, and I can't do annotations now. What is the problem? All right, I'm not going to be able to draw on, there's a problem. Can you guys still hear me?
Yes.
Because I've got this network issue icon, so I can't write on the screen. So I'm just going to have to, I guess I could use the, oh, that'll work. Okay, I can't use my pen, but I can use the, oh, there we go. All right. So let's look at elements, compounds, and mixtures at the atomic scale. So A, what do we have? Do we have an element, a compound, or a mixture?
Compound.
Mixture.
We have compounds, yes. We have more than one.
Yes.
Yes, we have more than one. So if we have more than one compound there, then we have a mixture. What about B?
Element.
Element.
Yep, just an element. There's only one thing there, and there's nothing bonded together. So that is indeed an element. What about C?
Compound.
Mm-hmm.
Compound.
Very good. It may not look like there's two different atoms there, but there definitely appear to be. Dark blue and sort of lighter blue. So yes, that one would be a compound. So mixture in A, element in B, compound in C. Great job. So this is one of the big things in chemistry that we're going to keep coming back to over and over and over. Law of mass conservation. What does that mean? So you remember when I was blathering about energy being conserved. We can't create energy and we can't destroy energy. It just gets converted from one thing to another. Same is true of mass. You can't get rid of it. You can only change it from one thing to another. So if we do a reaction, if we do a chemical reaction, where we have, what do we call the things on the left side of a chemical reaction? I'm sort of given away here. Things on the left side, what do we call them?
Reactant.
Yeah, reactants. They're going to react with stuff. So these are the reactants. Oh, damn it. These are the reactants on the left.
Mhm.
Here are my reactants. And they're going to make a product. Here's my product over here. So basically, after the reaction, just like I sort of, when I remember, I think we used the beer bottle example. If I was brewing beer inside a bottle, which is kind of a stupid thing to do, but if you're going to do that, actually, if you're making champagne, that actually is even better. You actually do make champagne inside a single bottle. You add more sugar to the wine that's in there, and you add some yeast, and you let it sit, and then it undergoes a second fermentation, and it makes bubbles. That's how you make champagne. So whatever mass of sugar and yeast I put in there, it's going to be the same when it gets converted to carbon dioxide and additional alcohol, is the same. And it's the same thing here. If I take a certain amount of calcium oxide and I react it with a certain amount of carbon dioxide, when that reaction, if it goes to completion, the amount of product I get will be exactly the same. The mass will be identical. And it doesn't seem like that's going to be the case, like when we're burning something, like, you know, if you're around a campfire and you have all this wood and then, you know, you burn it and there's nothing left but like a little bit of ash. Well, you have to calculate all the mass of CO2 and all the mass of water vapor that was converted and all the other sort of gaseous products that were created and then sort of, you know, went off. If you took all of that and added it together, you get precisely the same mass as the wood you started out with. And so that is always the case. And we can use this, actually it's really helpful, because we can use this to calculate how much product we should get. Because if you're a chemist working in a lab, and some of these reactants are like insanely expensive, and I have made this error myself. If you order like way too much, your advisor is going to get super angry, because things that we used to order in the lab cost like hundreds and hundreds of dollars per milligram, some per microgram. So if you were to order like, you know, 10 or 100-fold too much, that would like basically shoot your whole budget for the month. So you got to be really careful. So, but if you know how much product you need, if you know how much product you're looking for, you can calculate exactly how much reactant of each one you have. So if one is really cheap, one is really expensive, you can avoid spending all kinds of money that you didn't need to spend. All right, how do I get, oh, there we go. So this just shows again the law of conservation. So I've got two solutions here. Got a lead nitrate solution, don't want to drink that. I got a sodium chromate solution, don't want to drink that either. And when they're separate, I measure the mass, and then I pour the sodium chromate into the lead nitrate. You get this really nice reaction. How do we tell a reaction took place? Anyone tell me?
Color
changed.
Color changed, that's right. What else?
Gas coming out.
I don't know if, I can't tell if the gas may have been produced. I don't think you can see, if you can say that for sure here.
Precipitate.
Something else happened.
The precipitate formed.
Yes, very good. Ooh, man, knows all the knows all the jargon. Yeah, precipitate. There's a precipitation. You can see at the bottom here, this solid stuff is like falling out of it. But even if you couldn't see that falling back, you could still tell a precipitate form because it's not clear anymore. Notice how this solution, the lead nitrate solution, is clear. This sodium chromate solution is clear. You pour them together, it's not clear anymore. You see, it's cloudy. And just the fact that this is cloudy tells you that a precipitate. So a precipitate is just the formation of a solid, right? A precipitate is just a solid. And then we say it's a precipitate because it falls down. It falls out of solution. It may not fall, you know, super fast. It may be kind of not very dense precipitate, which it may just stay floating around in the solution for a while. But it is a precipitate. So there's two things that happen. The color changed and the precipitate was formed. Two indications that a chemical reaction has happened. So this is another sort of law we're going to need to learn. And basically what it says is that atoms are put together in definite proportions, meaning we don't have atom one. If we take two different samples of the same thing, we're going to find the same proportion of atoms in each. So here we're looking at octane, which is the most common carbon hydrocarbon in gasoline, and is, man, I wish I could use my pen. Here we go. It is, oh, damn it. Let me go back. Why can't I use my pen? It is C, this is really tough to write with your finger, C8H18. That's the formula for carbon. And so when you look at, so for every 8 atoms of carbon, there's 18 atoms of hydrogen, okay? So if I take 3 different samples and I figure out how much carbon and how much hydrogen is in each one, the ratio is going to be exactly the same. The ratio is always exactly the same. Now, I just told you that C8H18 is the formula. How come the mass ratio has more carbon than hydrogen? What's up with that? I said there's more hydrogen than carbon in there, but the mass ratio tells me there's more carbon than hydrogen. Why the difference?
Carbon atoms have a greater mass than hydrogen.
Yes, exactly right. Carbon atoms are much bigger than hydrogen. Hydrogen atoms are super tiny. They only weigh 1. Carbon atoms weigh 12. Every carbon atom is 12 times bigger than hydrogen. So if you look at the mass, there's going to be more carbon in there. But in terms of number of atoms, there's more hydrogen. But that ratio is going to be constant. And that's what the law of definite proportions mean. You're always going to get the same proportion. If you get a different proportion, it means you have a different molecule. And that's what we're talking about here. Here, if I burn carbon in the presence of oxygen, I'm going to form a number of different compounds. I'm going to form 2 different carbon oxides. And we'll learn about how to name things a little bit later. Oxide just means that I've reacted something with oxygen. And so notice that one of my oxides has 51% oxygen and 43% carbon, but my other oxide has 73% oxygen and 27% carbon. So because I have 2 different proportions, that means those are different molecules. They can't be the same. And when you drill down, you notice that one has a single atom of carbon and a single atom of oxygen. That's carbon monoxide, mono meaning 1. And the other one is carbon dioxide, di meaning 2. And so any time you look at carbon dioxide, it's going to have 73% oxygen, 27% carbon. And anytime you look at carbon monoxide or monoxide, it's going to be 57 versus 43. So sometimes if we just have one product, doggies next door barking, anytime we just have one product, we're going to have a single proportion. If we have 2 different proportions, it means we have 2 different molecules. Okay? So I think I'm going to leave it right there and ask if you have any questions, and we'll pick this up tomorrow, because it is Wednesday, right? I don't even know what day it is anymore. Any questions? I'm still here. Are you guys still there?
Yeah.
Okay. You asked all the questions at the beginning of class.
Just wondering, are you going to post up the lectures online?
Yes. Yeah, I just need to edit them. And so what I'm going to be doing is using Friday when I have time to edit all of them, put them up. So there's going to be a delay from week to week. So they'll be put up at the end of the week. It takes a while to get through all of them. And
Okay.
believe me, I don't want to look at them. I don't want to look at myself anymore. So I got to drag myself to do it. But yeah, I do that on Friday. Then they'll be posted by the weekend.
Okay, Professor, I have a question. For the grade, I noticed in the syllabus you just mentioned that the final exam has 200 points, and for each exam.
Yep.
But I mean, for the final exam, how much the percent for overall, and for lab report, how much for overall?
Oh,
For the grade, like.
yeah, I haven't calculated it. I think it's the final is around 20% or so. The other tests are about 25 to 30, and then the lab reports and the recitations are like half.
Okay.
Something like that. I can work it out. Yeah, I just didn't work out the proportions. I just told you to just add them all together. But I think those proportions are something like that. So let's say, yeah, so the final, if you're going in with like a B and you really crush it, you can pull an A. There's not a problem. And if you go in there with an A and you completely bomb it, you're not going to fail. So I think having it around 20 to 25% of the total mark is pretty good. I don't think you want it to be any more or really any less, because some people just get so freaked out by finals that, I've seen people with A's just do a swan dive. And on the other hand, I've had other students who had like a C that's like go in there, just like study their ass off and like, wind up with like a high B or an A. So I still wanted to change that much.
Okay, and for the final, it's gonna be accumulated or just the rest of the chapter?
The whole thing, yeah. No, it'll be from the start to the finish. So the first test will be like the first 3 chapters, and the second one will be the next 3. And I think we may have like a small exam just before the final, but the final will be on everything.
Okay.
Yeah. Okay, I will see some of you tomorrow afternoon, and hopefully I'll see a lot more of you tomorrow evening. Have a good night.
Thank you.
Thank you.
Thank you.
Thank you.
Talk to you later.
Thank you.
Bye. Have a good night.
Thank you. Have a good night.
Bye.